So the last application to calculus is one called hydrostatic force. It basically means what's the total amount of force if you take an object, typically a plate, and you place it under the water. So this is the generic formula. The reason there's two versions is because of Americans. If you use pounds and feet in your measurements, then you're going to use this top formula. And that 62.5 is a magic number that I'm telling you. And if you want to know what it represents, did you know that there are 62.5 pounds in a cubic foot of water? Because we're going to be looking at the pressure of water. And basically, it's like the weight of water on top of something, that's its pressure, right? And so we're trying to find out the total force acting on it, just kind of adding that up over a square footage. So it's 62.5. If you go like the rest of the universe, you go metric. Okay, the number's not as pretty. In fact, the number's split into two. Do you know where the 9.8, 9.81 comes from?
Force of gravity.
Yep. Do you know where 10 to the 3 comes from? And we're talking kilograms and meters now. It's the weight or the mass of a kilogram of water, a cubic meter of water, which is massively big. You wouldn't think it was so big, but darn it, it is. Right. So these are just magic numbers. You just remember them and you write them down when you need them. After you get rid of the magic number, the formula is the same. It's very cryptic because that's the way I've written it. To find the hydrostatic force, you find an integral from a start position of x to a finish position of x. And the expression you integrate is the depth at position x. And hopefully that'll make more sense once I start doing some examples. And the width of the strip at position x. So there are 4 questions. Here's the first one, similar to question 1 homework. I'm going to, if you just hold off a second, I'm going to mute you all because I'm getting some kind of background sound. There we go. So where was I? So we are going to look at our first example is we're going to find what the total force acting on this metal plate is. Now it's placed 1 foot below the surface and the plate is 6 feet by 12 feet. Now, since these are in feet, we're using that magic number there, right? 62.5. If this was 1 meter by 6 meters by 2 meters, then we'd use this 9,800 magic number, right? So you just have to know pounds is the top one, right? Meters is the second one. So you got your little picture. And what you do is you pick a random little baby strip. Yeah. And you measure the distance to that strip from the top of the plate. And this is the guy I'm going to call X. So from a random strip on this shape to the top, I'm going to call that distance X. Now, this strip is what we're talking about here. So when I say to you, what's the depth at position X, we're talking about how far under the water is that strip and in terms of X. Now, do you notice it's 1 foot plus another X? Are you happy about where the X plus 1 came from now? Now, when I talk about the width of this strip, how wide is this strip? Well, would you agree that its width is the same no matter where the strip is, right at the top, in the middle, at the bottom? Isn't its width still 6 feet wide for this shape? Now that does change in later questions, but for this question, it's 6 feet. So you want to get the force, 62.5, the integral. Now A and B represents the values of X at the top and the bottom of that shape. So at the top of this shape, x could be 0. And at the bottom of that shape, it would be 2. Would you agree this shape? 0 to 2. So that's what these two fillers are. Depth at position x is x add 1, multiplied by the width, which is 6, dx. And that's pretty much the hard part over. The next few lines are just tidying it up, doing what we need to do. And so what's it going to be? It's going to be 62.5, the integral from 0 to 2 of 6x plus 6 dx. It's going to be 62.5 power rule. Now, this I would do in a calculator. So it's going to be what? 3 times 2 squared. I guess I don't need to do this bit in the calculator. Take away a whole load of nothings. That's 12. Oh, and 12, that's 24. So 62.5 times 24. And the answer I get is 1,500. Are we cool with that? And if you're interested in what the units are, not that you really need to because they fill it in for you, it's that one. Now, if that wasn't bad enough, there are more than one correct version of how to set this question up. I decided to call x the distance from the top of the shape to the strip. And the reason I do that is that I do that pretty much for every question. Right? But you could describe x as the distance from the top to the bottom. Now, if you called that x, this integral would change, but the final answer won't because it's still the same question. So what does that mean? It means that when you're doing these homework questions, if this is right, it really doesn't matter which version, because sometimes there's actually 3 versions. Sometimes you measure x from the bottom of the shape up, which seems strange, but sometimes you can do that. And since there's going to be 3 versions and you don't know which one WebAssign is using, if you get this answer correct, you're right. You don't need to worry about, changing this to suit theirs. Because I'm just looking at their solution right now, and in this particular example, they counted x from the top to that strip. But I bet you in the next question, x will be from the top of the shape to there. I guarantee it. So you see that the problem isn't how to do the answer. If you get that, call it good. I'll basically, if you get that answer right, I'll fix the points on the homework so you don't need to worry about it, okay? Any questions about that first one, apart from the fact I ranted on about WebAssign having 3 versions, but you only see one of them, and it might not be the one that you picked. We good? Going to move this one to the next guy. Here we go then, number 2 coming up. This time it's going to be a triangle under the water. 3 feet below the surface, the triangle is 6 feet by 8 feet. Since it is feet, we know we're using that guy. It's going to be the integral from a start to finish. And it's going to be the depth and the width dx. Okay. I'm going to make my little strip here. And I'm going to call this distance from the top of the shape to here I'm going to call that X. And I do that with every question, which is why I prefer to show you the same method for each shape, regardless if it's a rectangle or whatever, right? Now, where are we going next is, where is that strip? Well, its depth, would you agree it's X add 3? Comfortable with the depth, right? From the top of the water to where that strip is, in terms of X, is X add 3, which means that I can go 62.5, the integral of X add 3. Now, won't X start at 0 and finish at 6? Are you happy where the 0 to 6 comes from? Right. At the top, X would be 0. By the time you got to the bottom of the rectangle, wouldn't X be 6? Now, the only guy that's missing is going to be the guy that's going to cause us trouble. How do we get the width? Now, I'll call that little guy W just for short. We're going to have to use a technique. I don't know the last time, if ever, you've seen this. It's called similar triangles. There's a property of shapes called similar triangles. And what it says that if you have two triangles that are the same shape, just one is like a larger version of the other, then it's described as corresponding sides are in equal ratio. Has anybody ever heard of similar triangles in the thing I just mentioned? Right, so I got a couple of nods, so it's not totally strange. Now, in this picture here, the big untouched rectangle is 3 feet by 6 feet. The little baby rectangle, that blue side is basically the W. Now, how much is this side? Well, isn't the distance from there to top to bottom 6? And isn't the distance from there to there a little X? So can you see why this is 6 take away X? Do you see where I got that from?
Then it's 6 by 8, not 6 by 3.
No, the 8 is how wide it is, the 3 is the depth. So what's the 6 by 3? What you? I'm not sure what the question is.
I think he's asking on the large triangle, should
Yes.
there be a 3 on the top?
Oh, there should be an 8 on the top.
Yeah, that's what I was saying.
I
Yeah.
totally agree with you. There should have been an 8 on the top. 8 on the top, 6. And the little guy is W by 6 minus X. Are we okay with that guy? Now, according to similar triangles, which these are, if you take 8 and divide it by W, you get the same answer as 6 divided by 6 take away X. Now, what that allows us to do is, with a couple of lines of math, shouldn't we be able to find out what the width is, right? What W is in terms of X? There's a little clue to what I'm going to do next. What shall I do next?
Cross multiply.
So 6W is 48 take away 8X. And then would you agree, divide everybody by 6? That's 8, and that's 8 6, which is just another way of saying 4/3. Which means I now have 8 take away 4/3 X. So because it was pounds, the magic number is 62.5. The way that we've constructed this, the X at the top of the shape is 0, and at the bottom of the shape it's 6. That depth to the strip is X plus 3. That width, eventually we found out, was 8 take away 4/3 X. So the next few lines are really us just doing the usual, whatever it is you need to get the answer. Right, that's a distribute thing. Good grief, what's that going to look like? 8x, take away 4/3 x squared, plus 24, take away 4x. That's the FOILing. So that becomes 62.5. The integral from 0 to 6 looks like 4x, take away 4x thirds x squared plus a 24. It's going to be 2x squared, 4/9 x cubed, and a 24x evaluated at x equals 0 to x equals 6. And I'm just saying dot, 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 right? Isn't it just number crunching? Plug in 6, get the answer. Plug in 0, which is nothing. When you plug in 6 and get your answer, then multiply it by 62.5, and whatever that number is, that's your force. And you are done. Are we good? I believe the answers are rounded off to the nearest whole number, so that's fine. I'm going to move this in a few moments. Is there any questions about that one? Or are we good? There's only 4 questions and I'm only doing one more. Because the last 2 questions are very similar to each other. So if I do one, you kind of know how to do them both. And so here we are. There, do you notice that this one's in meters? Right? So when you're in meters, isn't the magic number this fella? So the force is going to be 9.8 times 10 cubed. Very often called rho and G if you're interested. The integral from A to B, depth, width, dx. So one more shape. There's actually 4 ways to do this one. I'm still doing the one I always do, but there are 4 ways to set it up. You get the same answer. So I'm going to do a random strip. It's here. And forgot what color scheme I'm using now, try to be consistent. I'm going to call the distance from here to the strip, right? The top of the shape to the strip. I'm going to call that x. And so the depth is going to be this distance. And would you agree that the depth is x plus 4? Have you noticed that the way I do these questions, the depth is always x plus 2, x plus 4, x plus 10, right? Depends how far under the water the top of the shape is, right? So that shouldn't be an issue. Let's start filling in what we know. I have a 9.8 10 to the 3. The top of the shape will be 0 and the bottom of the shape will be 2 meters. Are you happy about the top to bottom, 0 to 2? So if you do it my way, 0 to wherever the bottom is, right? If it's 10 feet tall, it's 0 to 10. If it's 4 meters tall, it's 0 to 4. It's got a kind of similar shape. The depth we've already figured out. Now we need the width. See that little guy there? We need the width. So I am going to do similar triangles again. And we got a big triangle, which is 2 meters by 6 meters. And we get a little baby one, W by X. Now, although that isn't a side, the similar triangles, you're allowed to use heights and sides. So corresponding 2 matches with X, 6 matches with W. A little cross multiply, and then divide by 2, which means we now know the width. Are we good about splitting the shape into similar triangles and then use the corresponding ratio thing to find out what the width W is in terms of X, in this case 3X? If that works out fine, then the next line will look something like this. 9.8 times 10 to the 3, which is just 9,800. The integral from 0 to 2 of 3x squared plus 12x. Might as well call that 9,800, get it over with. Add 1 to the power. Oh, that comes out nice. From 0 to 2. So what's that? 9,800 times 2 cubed plus 6 lots of 2 squared. Take away nothing. 2, 4, 8. 8 and 24 is 32. And 9,800 times 32, I get 313,600. So for those 4 questions, the only thing you're really that interested in is the number and the newtons. Well, let me show you one of the answers to show you kind of the way it's phrased and so on. Can you see my question 3? Is it on the screen, right? Do you notice it goes on and it talks about hydrostatic force and 9.8 and that? Do you notice that they've done and they've called it rho and g? Right? They could have just called it 9.8 times 10 to the 3, right? And call it good, but that's fine. What's 9.8? There it is there, right? Now, in this case, you see it is 0 to 2, so they are doing it my way. And what would I have? I'd have an x plus 4 and a 3x, I guess. So you would do x plus 4 brackets 3x, not with capitals you want. And then you just type in here 313,600. And you're good to go. Now, what's going to happen is that in some of these questions, it won't be 0 to 2 because the way they measured x might be the bottom up or from the top of the surface to the strip, right? It's always to the strip, but you can pick who you like for x. If I return back to my shape, I'll show you different orientations of that same question. And then just don't worry about it. If I wanted to, couldn't I have decided to call that distance x? Now, do you know that would change all the algebra? And it would change the start and finish value. I could have decided, couldn't I, if I really wanted to, couldn't I have called that distance x? So you can measure the strip from the bottom of the shape up to the strip, from the top of the shape to the strip, which is the way I always do it, or from the top of the water to the strip. Now, each time you choose a different x, you know that the depth is now going to be different. You know, the x's will be in a different form because of that. And the width will actually be different. What won't be different is the final answer is the same answer. So why don't we just have a rule? Measure X from the top of the shape and call it good, and ignore WebAssign because sometimes it doesn't do that. That's the end of that question. Are we good? Any questions? The fourth one's just another triangle. Last chance. I don't know if that went well, but at least I hope it went, I could do it, right? I might not be 100% happy with it, but I could do it, right? That would be a success. So we're now starting chapter 9. In particular, chapter 9.1. What are called differential equations. Give you a big picture before we get into any kind of the details here. If you intend to do engineering, you will find that you will spend quite a lot of time and effort with differential equations, essentially solving them. You know, equations have x's in them or whatever, and you're trying to solve. So it's an equation situation. They are very, very important because they are models, formulas that can be used in many different ways in mechanical, electronic, any kind of engineering you could think of. Maybe not so much computer science, but maybe even there if I looked hard enough. It's that important that Olympic College does an entire class called Differential Equations 1, followed by Differential Equations 2. So you can imagine if you get 2 entire classes on just one topic, it's a pretty important and big topic. We're just going to give you a taster of it, right? If you do, hopefully you will do Diff 1, which is what we call it for short, you'll get into a lot more detail than I shall. Has anybody looked at their schedule and saw that differential equations was on it? You know, your advisor has said this is what you need to do what you want. Has anybody seen that or looked far enough ahead yet? Okay, Brendan, what was the advice you were given? To take one or take both or what?
Take both.
Right. So any of the engineer guys amongst you, it's going to happen. Now, if you're not an engineer guy, then I guess it's not so important. So let's talk about what is a differential equation. And this is a really bad definition, but it's true. It's an equation that contains, wait for it, you could have guessed that, but I'm doing it formally, right? A differential equation is an equation that contains derivatives. Here's an example of a differential equation. There's another differential equation. There's a differential equation. There's another one. Any equation that has a derivative in it is called a differential equation. So I'm going to introduce you to some nomenclature, right? How we name differential equations. The first major part of a differential equation is the highest derivative that's in it. In this case, it's a first derivative, right? Another first derivative, another first derivative. But in this case, isn't it a second derivative? Y double dash is just a second derivative. So we call these first order. And nobody ever writes differential equations. We all call them DE for short. So this is a first order differential equation. So is this, and so is this. But this fella is called a second order differential equation. So when you are looking at solving a differential equation, before you start getting into the nitty-gritty of how you're going to find the answer, the first thing you have to identify is what kind of differential equation am I looking at? And there are first order, and there are second order. Can you imagine what a third order differential equation might look like? Won't it have a third derivative in it somewhere, for example? Now, we're not getting into too much of the details because that's what Calc Diff 1 and Diff 2 are going to be about, but I will introduce some other terms that you should be aware of. When you are dealing with differential equations, there are very often particular versions of equations that you solve in one way. You know, like some integrals you solve by integration by parts, whereas other integrals you solve by substitution, right? U-subs. And although we don't call it that, couldn't we say this was a U-sub integral and this was an integration by parts integral, right? If we gave you that name in front of the question, wouldn't that be very helpful in how you're going to solve it, right? Well, very often differential equations, there's families of them where you solve them the same way. So you'll find out in this class, at least, a couple of the major ones. There's going to be variable separable differential equation, and the other one's going to be called linear differential equations. And we are going to solve those particular types of differential equation, but that actually comes in to play towards the end. We don't do that right away. So recap, a differential equation is an equation that has a derivative in it, and we name the type of differential equation by the highest derivative. And it doesn't matter if there are x's anywhere. And differential equations are still differential equations. Right, so don't get into it. I just noticed that a lot of my questions didn't have much in the way of x's. So far, so good. Now, let's take a very simple differential equation. Why don't I just take that one, because I've written it down, and look at solving it. Well, if I tell you that dy by dx is x cubed, how do you think I could find y? I know the derivative of something is x cubed. How would I find the something?
Maybe by taking the integral.
You do. So in simple differential equations, which these are, they'll be first order, but they could be higher. You would integrate. Does that seem reasonable? That you're basically undoing a derivative, right? So undoing it is integrating. Now, when we do that, it's a power rule plus c, right? This is called, right, the general solution of the differential equation. And it's called the general solution because It's got a plus c in it. Suppose it was the same question, but I also told you this. The value of the function when x is 0, that's what y of 0 is, right? When x is 0, y is 10. Well, if I take my general solution and I plug in 0 for x, and I know that's 10, would you agree that c is 10? And that makes my solution now a little bit more detailed. And this fella, he is called the particular solution to a differential equation. This is pretty much the language of differential equations. Once you get into it, you'll say, oh, I solved a second order differential equation, and I found a particular solution, or I found a general solution to a first order variable separable differential equation. So you talk in that language, other people who know differential equations have a pretty good idea of what kind of differential equation you have and what kind of solution you're telling them. So if there's ever a plus c, it's a general solution. If you're told a piece of information that allows you to find the c, it now becomes a particular solution. Let me wind back to the general solution. So you've got this differential equation. Oh, and by the way, it can also be written like that. Would you agree that's the same thing written in 3 ways? Right? That's not a biggie. And you found its solution, which for some reason I've decided to call f of x. Now, what would that look like? Well, if you try to sketch on your calculator 1/4 x to the 4 plus c, what you could do is just take a little snapshot. Oh, I'll try c0, c is 1, 2, 3. I'll try c is -1, c is -2, and c is -3. And if you did that, you're going to have to trust me a little bit. But that's what it would look like when c is 0. And this is what it would look like when c is 1. And this is what it would look like when c is -1. And this is what it would look like when c is -2. Can you imagine doing every possible c on the universe and plotting it on this graph? Instead of having a single function now, don't we have a kind of model, I don't know, of some wind blowing around a corner, or some river that had a kind of, at this piece of the river, there's a kind of swirling current going on. Do you see a differential equation could be used to model a dynamic situation, right? A current, a wind pattern, all sorts of cool things. So they are very useful at modeling. Now, what happens when you tell me y of 0 is 10? Aren't you basically just telling me one point? But once you tell me that point, doesn't the curve have to pass through it? So if you tell me any point, if you tell me the coordinates of that point, won't the particular solution be this one curve? The general solution is all of them. The particular solution is just the one that you get that has this point on the curve, which is kind of unique. Just checking how much time we got. Are we doing good so far? You like differential equations, at least what you've seen? Haven't done too much yet. For the last question for today, let's do a second order differential equation. And I'm going to write it as y double dashed as e to the x plus x squared. And I want to find the general solution to this differential equation, right? General solution, right? The one with the plus c's in it. So if you integrate this once, won't that be what y dashed is equal to? So you integrate it and you get this guy plus c. So it's just like we did with the first order. I integrated. How do you think I'm now going to get y? Which is the solution that we're looking for.
Just do it again.
Just do it again. You got to be a little bit careful because this isn't something you typically would even think about. That's good. Okay, that's a 12th. Right, here's the funny stuff starting. That is there now. That is a physical constant, right? It's like plus 5 or plus 55. It's there. You can't ignore it. What is the integral of plus c if c is just an unknown constant?
Cx.
Agreed. Now, when you integrate things, don't you finish with a plus c? Well, you can't finish with a plus c because it's used, so you finish with a plus d. Why am I making these two different letters of the alphabet?
Because they might have different values.
Exactly. Yeah, an arbitrary constant could be, that's 10, but this is 50, right? Could happen. Right. So that is the end of that question. That is our general solution. I'm not doing it, but if you wanted a particular solution, wouldn't they have to tell you things like y of 0 is 7 and y dashed of 0 is 11? And if they told you that, wouldn't that allow you to get the C in the D? And that will happen, but not today. Say hi, everybody.